Hello, everyone. Elizabeth Klein here with the NESDIS Geo program, and welcome to the Satellite Book Club seminar series, session number 233. Today's presentation is Measuring the Ocean Winds with Synthetic Aperture Radar, or SAR. It is presented by Tyler Ruff, a senior programmer analyst with the Synthetic Aperture Radar Group in the Satellite Oceanography and Climate Division, or SOCD, at NESDIS SAR. Our facilitator today is Aaron Jacobs, Senior Service Hydrologist at the NWS Weather Forecast Office in Juneau, Alaska. I'd like to remind all audience members that this session is being recorded. Per OCIO Privacy Act guidelines, attendees will not have the ability to use their microphones or webcam. Please see the pin message in the chat for more information. There will be a Q&A session after the presentation. I would like to encourage attendees to post your questions in the chat room and they will be fielded from there. If you are logged in under an alias account, please sign in with your full name or specify your full name when asking a question in the chat. We are looking for future presenters. Please contact the Tower S team if you are interested in presenting. There will also be a form in the chat to submit any feedback. The training team can help create materials that may be unavailable. Contact Ross Bentile for information or questions about that. Thank you to the OCLO, the GEO and LEO programs, and our facilitator, Aaron Jacobs. Tyler Ruff joined NOAA's Office of Satellite and Product Operations in 2017 after working as a meteorological applications developer in the private sector for several years. He joined the Water Surface Conditions team within NOAA's Center for Satellite Applications and Research in 2019 as a senior programmer analyst, and has used his background in meteorology and oceanography to develop and enhance the team's diverse suite of products generated using satellite-based synthetic aperture radar with a specific focus on deriving accurate measurements of tropical cyclone-force ocean surface winds. Tyler's credentials include an MS in Atmospheric and Oceanic Sciences from UCLA and a BS in Meteorology from Penn State. Tyler, welcome to the Satellite Book Club.
Thank you very much for having me. Okay. Yeah, happy to be here to talk about measuring ocean winds with SAR. Before I begin, I just want to mention that Chris Jackson, who's my very close colleague, actually was originally slated to present here, but unfortunately he couldn't make it due to a conflict. So much of this presentation is attributed to him, so hopefully I can do it justice. Also want to mention our science team lead is Marilyn Murphy, who I believe is on this call as well. So with that, I guess we'll get started. So yeah, as you mentioned, we are known as a water surface conditions team within the Center for Satellite Applications and Research, which is STAR, but we often refer to ourselves as the Synthetic Aperture Radar Science Team because all of our products are derived from SAR, of course. Today's talk will mainly focus on ocean and lake surface wind speeds, as well as tropical cyclone wind speeds. You can see an example of that in the bottom left image. You'll see a lot more of those in this presentation. But I also wanted to mention we have many other products that we produce, including flooding and inundation maps, such as in the center image, and sea ice extent and characterization in the bottom right image. So just a brief overview of how SAR actually works. So first and foremost, it's an imaging radar. It can see through the clouds and operate day or night. It works by transmitting radar pulses and recording both the amplitude and phase of the reflected return signals. And these return signals are then coherently combined over a short time interval, i.e. the synthetic aperture, to produce a 2D image of radar backscatter. This is visualized in the diagram to the left here. We're seeing the Sentinel-1 satellite moving from left to right in its flight direction, orbiting at about 700 kilometers altitude. It is a right-looking SAR, so all of its pulses are sent out to the right, and that's pretty typical. It images in many different modes, but we typically use the ones to the right, which offer the widest amount of coverage. But the unique feature of SAR is that it uses the motion of the satellite itself to create the synthetic aperture, in effect creating a large virtual antenna. So for example, for Sentinel-1, since the satellite is moving at around 7 kilometers per second and transmitting pulses at about 1,000 times a second, when these pulses are combined every half second, the effective real aperture antenna length is equivalent to 3.5 kilometers in diameter, which is how it can achieve such high resolution imagery. So the latest generation of SARs have, improved so much since the first generation. I believe the first one that was specifically launched for ocean observation purposes was CSAT in 1978. Since then, there have been, many, many, many more. Typically, the ones that we use are polar orbiting. And these resolutions that we can achieve, they can get down to less than 3 meters in certain modes, or above 100 meters with a swath width as wide as 500 kilometers. As always, there's a trade-off between coverage area and resolution, and we typically favor coverage area for ocean surface winds. So the main satellites that we use are the Sentinel-1 satellite that I just mentioned. It's actually 2 of them, Sentinel-1A and Sentinel-1C. And Sentinel-1C was just launched last year and became operational 2 months ago. That's operated out of the European Space Agency. Then there's RCM, which is the RadarSat Constellation mission, which is operated out of the Canadian Space Agency. That's a constellation of 3 satellites, all identical, and they were launched in 2019. Both satellites have very similar characteristics, 12-day repeat. They are both C-band SARs, so they operate about 5.4 gigahertz, which is about 5.5 centimeters of wavelength. They operate in the same polarization, so vertical, horizontal, and cross-pole and compact modes, with very similar swath widths and resolutions. So upcoming, we have NASA's NISAR mission, which is slated for launch in June of 2025. Hopefully, it's been delayed quite a bit. But that will be an L-band SAR, and L-band operates at about 20 centimeters wavelength. So it will see different features than the C-band does. Before we can get to winds, we have to talk about the normalized radar cross-section, which also is known as NRCS. So that's the measure of backscattered radar energy, as you can see to the left here. That's an image of the NRCS off the coast of Virginia. You can see the land features to the left, and then the ocean features to the east. So the SAR is sensitive to roughness at the centimeter scale, which is very close to the actual center wavelength. And smooth surfaces scatter the radar energy away from the satellite and appear darker, whereas rough surfaces produce more backscatter, meaning more radar energy was returned to the satellite and appear brighter. So wind is the primary source for the centimeter scale roughening of the ocean surface. These are capillary waves, and the actual physics involve Bragg scattering, in case you're interested in learning more about that. But that's about as far as I'll go into the physics. But essentially, ocean surface roughness increases with increasing wind speed up to a certain point, and I'll discuss that later. The normalized radar cross-section is converted into wind through a geophysical model function, or a GMF. Now, these GMFs that we use establish the relationship between the cross-section, the wind speed, wind direction, and the actual viewing geometry of the SAR itself. If you're familiar with scatterometers, it's analogous to that. We actually use the same GMFs that the scatterometers use, mainly CMOD 4, CMOD 5, and we're looking at CMOD 7 right now. Scatterometers are similar. They also provide wind direction, which the SAR does not, but at a much lower resolution. So the image on the left is the wind field associated with the NRCS that I just showed using the CMOD 4 GMF. So let's just look at a couple more examples. So we get daily coverage over the Great Lakes, specifically with RCM coverage. The left image shows Lake Superior. I'm actually going to return to this example because we see a pretty interesting frontal feature there. On the right, we see Lake Erie, and you can see some dramatic winds there, up to about 50 knots, which is about the limit of how high CMOD 4 can produce accurate results here. So the winds can get pretty ferocious at certain times of the year of these lakes. Then we have some more examples of gap flow winds. To the left is the Gulf of Tehuantepec. This area is actually of interest to the Tropical Analysis and Forecast branch of the National Hurricane Center. To the right is an image over Southwest Alaska, which is of interest to folks up in Alaska, of course. In both these cases, we have gap flow winds with winds coming out of the north. As the winds flow through the topography between the valleys and the mountains, they get funneled into certain features, streaks and striations, as you see here. And the SAR captures these very well in high resolution. So, you know, these are pretty fascinating features here. So some characteristics of our wind products. We produce these at 500-meter sampling, which is just a little bit degraded from the native resolution. But it does mean that they are available adjacent right up to the coastlines, which is unique with the SARs. We report the wind values at 10-meter height above the surface, which is standard. We just use a scaling law. We have accuracy of less than 4 knots up to about 30-knot wind, and a 20% error on winds of 50 knots, which is about the upper limit of our standard winds product, as I mentioned. We produce these images with in near real time at about 2 to 6 hours latency. I would say more like 2 to 4 is standard, but depending on where the image was collected, where the ground station was, and if there's any network and connective problems, it can go above 6 hours latency at sometimes. So the revisit is very location dependent due to the orbit, the nature of the orbit. So at higher latitudes, it revisits much more frequently than lower latitudes. For example, over Alaska, we do get daily coverage, whereas over the Great Lakes and over the North American coasts, we see near daily coverage, whereas over CONUS and even for tropical regions like Hawaii, it can be 6 to 12 days for an exact repeat cycle. So as for caveats, so the SAR produces wind speed only. It does not measure direction like the scatterometers do. So as I mentioned, in a GMF, we do need the wind direction in order to calculate the wind speed. Okay, so we do obtain the wind directions from weather models instead. The main one that we use is a GFS quarter degree model, but we do also use the HER model, which is 3 kilometers over the Great Lakes. But this does mean that if the model reports an inaccurate wind direction, we would get an inaccurate wind speed. I'll show an example of that in the next slide. Importantly to know, maybe this is somewhat obvious, but we only record winds over the water surface only, okay? So no wind retrievals are valid over land, nor from the ice. I'll show examples of those. Also, other atmospheric scattering effects, such as hydrometeors, can produce invalid wind speeds as well, and I'll show an example. But before that, I just wanted to mention that the newest AWIPS preprocessor, the Tower Pro version 25, I believe, makes these SAR wind products available to all of the weather forecast offices and river forecast centers. So if you don't already have it and you're interested, contact your local AWIPS person for a subscription to these products. So as I mentioned, the wind direction plays a pretty important role in how we report our wind speed. So going back to the Lake Superior example with that front, I wanted to show how wind direction from the GFS and the HER will affect the actual wind speeds. So in the top right image, we're using the GFS model here, and we marked the true frontal boundary here in as a black line, which is accurate. Whereas using the HER model in the bottom right, it has the leading edge of atmospheric front west of the actual image location. This means that the incorrect model wind direction results in an incorrect SAR wind speed within the front. So, you know, we've got to be careful. We like the HER. It's a higher resolution. It's reported every hour. It's great, but sometimes it can get these fronts slightly wrong, whereas a coarser scale like the GFS might be more accurate, and vice versa. So another source of error can be from atmospheric scattering, such as hydrometeors. And these are fairly common behind the leading edge of the storm line. And so what we're looking at here is Lake Michigan, obviously. In this case, atmospheric ice in the melting layer produce anomalously high wind values that you can see here marked in the SAR winds, the radar cross-section in the middle. And then we also have surface-based Doppler radar in the right, which corroborates our suspicions in this case that the winds in this case actually were not winds, but they were atmospheric signals. So again, you got to be careful. If you do look at these images long enough, you'll be able to detect these automatically. We don't always have Doppler radar to compare against, obviously. But similarly, for deep convection, more typical of tropical regions or lower latitudes, you do get storm cells with very distinct ice signatures in them. So again, this atmospheric ice scatters a lot of energy, resulting in invalid winds, such as those red splotches on the left there. So as I mentioned, also ice can be a significant source of error when producing wind speeds. On the left, I've labeled all of the actual areas of lake ice over the Great Lakes. This was just in March. This year, we actually had a pretty decent freeze for once. Hasn't really frozen very much in the last couple of years. But you can see again that that the ice produces high backscattered returns, which are falsely translated into high wind values. So the colors over ice are just not valid winds. Same goes for sea ice. This is showing an image off the southern coast of Greenland here. Now, sea ice is a bit more tricky. It's incredibly complex. It shows up in many different forms in the SAR, but in this case, it's pretty obvious that these kind of wispy features, that's ice, maybe newer ice or melting ice. It's being drawn out by the ocean currents, but it will still show up as an invalid wind speed, as you can see in the wind image to the right. So there's a lot of other phenomena that are detectable by SAR. I've mentioned a few of them, and I'll mention a little bit more in a moment. But we also look at surface waves, wave spectra, significant wave height as well. We talked about sea ice, internal waves, things like that. And in the atmosphere, we do see a lot of convection, storm systems, vortex streets, etc., gravity waves. I did not mention anthropogenic sources really, but we can do ship tracking and oil platform monitoring. And we also do monitor oil spills or areas of surfactants as well. We do publish those on our webpage, but they're a bit experimental right now. As for coastal and land, we do have a pretty robust flooding and inundation detection program the last 3 years. We have a team working on algorithms to detect floods in SAR imagery. But the most important point here is that all of these atmospheric and oceanic phenomena modulate the centimeter scale roughness in very distinctive ways. So that leads to the pros and cons of SAR measurements. So we definitely have some advantages and some disadvantages. As far as advantages go, as I mentioned, the collection is independent of lighting and cloud conditions. It has a wide area of coverage, anywhere from 350 to 500 kilometer swath width. High resolution coverage, anywhere from 30 to 100 meters. Again, we report the winds at 500 meters. We see a wide array of atmospheric and oceanic phenomena that have distinctive signatures, as I just mentioned. But I think actually most importantly is that there's more SAR data available today than at any previous time in history. And almost all of it is available free and in near real time. It has just grown exponentially in the past few years. As for disadvantages, it does have a limited daily coverage. So because it's an active radar, it requires a lot of power to run. So it has a limited footprint and only covers a portion of every orbit. For example, Sentinel-1 collects for 25 minutes of every orbit. Typical orbit takes about 98 minutes, so it's only collecting for about a quarter of each orbit, which still results in about 600 scenes or granules per day. But that's why SARs are often launched in constellations to make up for these shortcomings. As I mentioned previously, the latency sometimes can be a little bit high. We're talking maybe 6+ hours. It really depends. You know, if you have a scene that was recorded and the ground station was, you know, a third of the way across the Earth, and then it has to transmit, it can take a while. But again, typically we see 2 to 4 hours. And to repeat the bullet point from the left, these wide array of atmospheric phenomena have very distinctive signatures, which means it can be a challenge to properly interpret. This is especially noticeable in C-band SAR imagery, which is what we use. Other bands have their own pros and cons, of course. L-band won't be as sensitive to atmospheric phenomena, but they might not detect as much features on the surface. So here's some more interesting features in the marine atmospheric boundary layer. I know Chris has done a fair amount of research on these phenomena, so I'll just go over some of these quickly. But you can see examples of lee waves, wind funneling, island wakes, atmospheric gravity waves, roll vortices, cold pulls. So, you know, all types of interesting phenomena exist here in the marine atmospheric boundary layer. So pivoting more towards the high wind regime. So what I'm showing here on the left is a typical polar low or mid-latitude or polar low. We see winds up about maybe maximum 50 knots, but that's about as far as our regular winds algorithm will be accurate. But on the right, obviously, is a different situation. And this is a SAR image for Hurricane Lee back in September of 2023, where we see winds up to 100 knots and even more. So how exactly do we do this? Well, first I want to mention that we do have in place a fully automated system to produce these high resolution, near real-time tropical cyclone wind speed products using SAR. And we provide these to the hurricane centers, such as National Hurricane Center, Joint Typhoon Warning Center, Central Pacific Hurricane Center, etc. And we produce many products relative to forecasters, such as fine resolution wind speed images. We give our standard 500-meter product, but also our 3-kilometer product. 3 kilometers is basically our way of simulating a 1-minute sustained average wind speed, which is of interest to the hurricane centers. We use a spatial average because we can't do a temporal average. It works fine. It's not perfect. We do produce radial wind profiles. I'll show a slide that shows an example of that in a moment. From those profiles, you can derive maximum wind speed, radius of maximum winds, 34, 50, 64 knot quadrant fixes. And of course, we can see the eye location and area very well when the SAR covers it. Importantly, so we have a dedicated geophysical model function for these winds greater than 34 knots, valid up to about 80 meters per second or 160 knots. In case you're interested, we actually use the cross polarization channel to derive these high wind measurements, which does not get saturated like the cold pole channel does. I also wanted to mention here that we did present at the Satellite Book Club session 60, where we did talk about our tropical cyclone wind program back in July of 2021. Back then, it was just starting up, and it was much different. We have grown so much since then. So it's fun to kind of look back upon that presentation just to compare with what we have now. So just an example of of just the plethora of tropical acquisitions we've received just over the past few years. And as I mentioned, in 2021, we would be happy with maybe a couple dozen storms at most. Just last year, we got 80. And already in 2025, if you include the Southern Hemisphere, we're up to 26 cyclones before the Northern Hemisphere season even started. On the right, you can see the footprints of all these tropical collections. In red is RCM, which makes up the large bulk of these. So why is that? So in 2022, the Canadian Space Agency updated their Hurricane Watch program to improve the RCM tropical cyclone acquisitions. So the result has just been a gigantic increase in tropical cyclone collection tasking and an increase in the number of eye hits that were obtained. So the accuracy of the SAR hits, because we have to program them a couple days in advance. And depending on the accuracy of the forecast, you might not hit the storm when you want. But RCM has just changed the game completely. This was just an image I created for another publication, but I thought it was really cool, just a cool way to visualize these storms. This is the 2024 Atlantic hurricane season, specifically the RCM collections. It just shows how often we can image these storms now, at least daily, if not twice daily, on the ascending and descending passes. Yeah, so it's just amazing. You can see Hurricanes Kirk and Leslie to the right. They follow the same track. Hurricane Ernesto goes up to the center, and Hurricanes Milton, Helene, and Raphael are all the way to the west in the Gulf there. So here's just some more close-ups of the most recent storms from the last season. Hurricane Kirk, which was a Cat 3 storm, was on the left there. Hurricane Milton, Cat 4, is in the center. And Hurricane Helene, which is Cat 3, is on the right. You can just see the differences in the eye structure, in the intensities, in the rain bands, in the size, the morphology. All of this stuff is just fascinating to look at, and it's an active area of research, of course. As I mentioned, we do produce hurricane profiles. So what we do is we split up the storm by quadrant, which is what the hurricane centers do. And if you plot the wind speeds in each of those quadrants as a function of distance from the center, you get these types of curves. So you see the eye wall, or the eye has the lowest winds in the middle, and then it shoots up. Then you get your Vmax, which is the intensity of the storm. And then from there, you can derive the different radius of winds at 64, 50, and 34 knots. Also the radius of max winds. So all of these statistics are of interest to these hurricane centers and are sent out in different formats. So here's just some really cool animation I wanted to show of a triple collection over Hurricane Helene. So 3 of our SARs collected this storm over the course of just 2 minutes, which shows the actual rotation of the storm and the wind fields in the Gulf, which I don't think this has ever been seen before, not on such a wide scale at least. Again, it just shows how many SARs we have, and these overlapping collections are so useful for validating our wind algorithms between all the sensors, because they're all calibrated differently. So I thought that was just such a cool image there. So as for final notes, just to summarize a little bit, as you've seen, SAR imagery can and is being used to create fine resolution wind speed maps of oceans or lake surfaces. Since we report the winds at high resolution, about 500 meters, they're available adjacent to the coastlines with an accuracy of about 4 knots. That's up to about 30-knot winds. But only wind speeds are derived from the SAR. And in order to calculate these wind speeds using the GMFs, we have to obtain wind directions directly from weather models or from other sources. This can add a source of error because an inaccurate wind direction can lead to an inaccurate wind speed, as I demonstrated over that frontal area in Lake Superior. And SAR winds are derived only from wind-roughened water sources. Just to reiterate, we don't get wind retrievals over land, nor from the ice. As we've seen, also atmospheric scattering, such as hydrometeors, can produce invalid wind speeds as well. I showed that a wide variety of marine atmospheric boundary layer phenomena are observable with SAR, such as convection cells, roll vortices, gravity waves, et cetera, et cetera, et cetera. The imagery can also provide tropical cyclone winds up to 160 knots or 80 meters per second with our dedicated cross-polarization GMFs. We worked on this over the last couple of years. We think that it's very mature right now, but it's still an active area of research. But these fine resolution wind speed images are being used to create these radial wind profiles to identify the Vmax and Rmax and all the quadrant fixes. And they're sent in real time to all of the hurricane centers via AWIPS and also ATCF, if you're familiar with that. It's also available on our website, which is linked at the end of this presentation. Our tropical cyclone program acquired 80 storms during 2024, including almost 400 I-hits. This is like an increase of 5 or 8-fold just since 2022, mainly due to increased TC tasking from RCM and Sentinel-1, which are tracking the system earlier. In the INVEST stage now, we do publish INVEST data, but we don't send those to the hurricane centers just yet. I also want to mention a lot of this information was compiled in these quick guides. These were developed back in 2020 by some folks at CIRA and some of the other weather forecast offices. There's a link in this presentation to that. We actually are planning on creating an updated version of this, of course, because it has been 5 years. So if anyone's interested, we will, once we work on version 2, we can send it to you. And with that, so my last main slide is just links to our actual SAR wind product pages on the left there, and some other resources if you're interested, and with some publications. And with that, that concludes my presentation.
Great, thanks, Tyler. That was a great presentation. Yeah, and so just remind attendees right now that please submit any questions into the chat room, and we encourage attendees to stay for the discussion and great participation possible from the field offices and our regional headquarters. We also encourage everyone to change their meeting layout to tiled and select high tiles without video. You're also going to see a post in the chat room about some Satellite Book Club feedback. Please provide some feedback if you can. And at this time, please stay tuned for any updates on any more Tower S teams meetings for next presentations. And if you are looking to get any Satellite Book Club configurations or satellite products, reach out to the Tower S team, Kashad Bowman or Emily Maddox. And so now we'll kind of see if there's any questions in the chat room and kind of go from there. So Tyler, there's a question here from David. Said that I found SAR data fascinating over the past several years. I looked at them over at Lake Erie. Great stuff. It seems like the LEO ideas eventually gets ported over to geostationary satellites. Are there any plans for future geostationary observation, lower res SAR, for continuous coverage rather than just daily, or rather, not work as a satellite geostationary?
Oh, well, you know what? Boy, it would be very interesting if we could have SAR as geostationary. But unfortunately, if I understand your question, yes, SARs don't work as a geostationary orbit. They need to move to create their synthetic aperture. And the SARs have to be LEO and 500 to 700 kilometers in altitude, pretty much, or they can be surface based. But I have not heard of any medium orbits or anything like that, or geo. But we would love that if that was ever possible.
Yeah, I would definitely agree to that. Here's another question from Stephen Corfity. Nice presentation. Can hydrometeors and tropical cyclones affect observations from the SAR speeds?
Thank you.
Oh no, can hydrometeors and tropical cyclones affect the observations from SAR? speeds?
Yes, sure. Sorry, I didn't get the question. They certainly can. This is a good example here. So if you see, I guess the center image here, Hurricane Milton, you can see in the outer rain bands here that these are not actually surface winds. These are most likely due to hydrometeors, for example. And it is tricky because, you might think, well, in the core of the storm, you do get some deep convection as well, but it kind of has the opposite effect. If you look very closely here, I don't know if you can see my mouse, there's an area right here with low wind speed in the northwest quadrant. That is most likely due to rain attenuation. So at certain times and certain conditions, the satellite or the SAR will be attenuated by very intense rain bands. And you can see these lower areas which are not actually representing the winds. So you do see these features all the time. It's actually an extremely active area of research within our own group to try to be able to flag these, because oftentimes you can get an incorrect wind reading just due to ice, as we've seen in the rain bands, or these attenuations. So yeah, we're looking into other ways of flagging these. Let me see if I have any other. I don't quite have an example, but I have other presentations where I can send you some of the analysis that we've done that goes into that more specifically.
Okay, great. Yeah, that's very interesting. That example you're showing how there's less winds in that quadrant where you would suspect that it would be more continuous in that attenuation. We got another question here from Matthew. What name of the AWIS package was it that you were mentioning?
Let me go back here. Well, so what I know is that the AWIS preprocessor Tower Pro version 25. I don't use AWIPS myself, so I can only comment on what I've heard, but I do understand that SAR winds should be available within this version. If anyone else wants to join in, yeah.
I would contact the TowerS team if you're looking for these SARs into AWIPS. Me here locally in Southeast in Juneau, we have it just recently with that update. So it's very beneficial to our forecasters, of course, to have it in our AWIPS, and we really appreciate all the efforts to get that to us. Here's another question from Felipe. Great talk, Tyler. I have a question about the GMFs varying from using the one based on the CMOD 4 that is really only good at 50 knots versus the cross polar GMF that's good up to 60 knots. What are the critical differences between these two GMFs? And then does the cross polar data allow you to get some directional information so it's less reliant on NWP models with wind directions? How much, if any, does the center position of the SAR pass matter to the tropical cyclone winds and cross pole GMFs?
Okay, great question. I'll try not to take too much time here. Yes, the copolarization GMFs. So the copol is VV or HH. You transmit in vertical, receive vertical, or transmit in horizontal, receive horizontal, right? The issue with that is that the signal does get saturated. The NRCS gets saturated, and if you convert it to winds, it's about 50 knots. We do need the directions to solve the complicated equations to compute the copole winds. The advantage of the cross-pole GMFs are that they do not require any external wind directions. You can actually infer the direction directly from the polarization itself. In case anyone wasn't familiar, cross-polarization means you would transmit a vertical signal and measure the horizontal response, and vice versa with horizontal and vertical. So we do not need any weather models for that. So in some ways, it's actually a more simple GMF. It uses lookup tables and things like that. It is empirical, but it is a little bit harder to verify than the regular copol winds GMF. So you're exactly right. We don't need any weather models for our cross-pole GMFs. I believe your second question was about, does a storm center make a difference? Let's see here. Go to the slide. So yes, it certainly does when we're recording all these statistics for the storm. So in the bottom left here, you can actually see there's like a cross right here, which shows the center point of the storm. And what we need to do is we need to accurately mark this center point in order to derive all of these other statistics, okay? And this is actually very tough to do. We have an algorithm that uses an initial guess, and then it kind of interpolates into the center point. But sometimes it doesn't work if you don't have a symmetric eye wall, or if the storm is kind of misshapen for any other reason, or if it's too weak, or if the eye is extremely small. And then we have to go in and correct it manually. So I'd say about 70% of the time it's accurate. Otherwise, yeah, we do need to do some manual correction. So, but to be clear, the storm center does not have any relevance to the actual tropical GMF. Okay, the GMF operates independently of knowing anything about the storm itself. So that's the main difference, and I hope I answered your question.
All right. I got one more of like my own. You were talking about this other SAR products, and you saw in the list of like the significant wave height and wave spectra. Do you know if there's any products being developed for the end user for those types of detectable phenomenons from SAR?
Mm-hmm. Yes, yes. So you guys can tell I probably skipped through some of these, but yes, we do. At one point early on, and I'm not sure if we still do this, but there was an active area of research into significant wave height. Chris or Frank, who's on this call, can probably talk a lot more about that than I could, because I wasn't around with those discussions. But we have produced wave height and wave spectra products. We do have an active oil spill detection program, as I mentioned. We have a couple algorithms, and we post those to our website. And as I mentioned, Chris has done research into internal waves and gravity waves and all of these things. There are papers out there that discuss these topics as well. Let's see, as far as flooding and inundation, that would be a whole other topic that I could talk about. And it has been a really, really, excuse me, there's a truck right outside. It's been a big effort in our group just in the last 3 years to come up with an algorithm to detect floods automatically. But we do actually do this on a real-time basis. It's not quite fully operational. It hasn't been incorporated into OSPO yet or anything like that. At one point, we did do ship detection. That product is not quite, I don't think it's being produced anymore. I think other groups do that as well. Let's see, is there anything else on this list? I would say, I mean, burn scar identification, land deformation. So we don't do interferometry in our group itself, but SAR is famously known for interferometry. So I can, at the end of this presentation, all these links will lead you to some further information and publications on some of these products, and you can actually see not just the winds, but we have Great Lakes. There's oil, there's ice motions that we produce as well, and yeah. So there's a lot of other things that we do in our group, but winds is kind of our core product.
Great, awesome. And before we close out here, I just got one more about talk about the latency of these products to the end user. It was like 2 to 4 hours, 2 to 6 hours. Do you think there's a way to reduce that latency? Maybe direct broadcast, but I know you have to have a certain antenna, I think, on the satellite.
Well, there's not much we can do about the transmission of data from the satellite. The satellite orbits, has a recorder on it. SAR takes up a tremendous amount of data, a couple terabytes every day, at least for one SAR, beams that down into several ground stations. And it can take some time because the ground stations are not always in view of the SAR. So as I mentioned, there are certain passes, specifically some of the ascending ones that might pass kind of over the poles and things like that, where it might not receive, or in the Southern Pacific Ocean, it might not come into contact with a ground station for, a couple hours or an hour at least. And then all of this data has to be ingested, processed. It's level 0, and transmitted to the ESA and European Space Agency. They produce level 1 products out of that, and then they make that available. So all of that, you really can't get much better than, in emergency situations, maybe an hour by the time the SAR image gets to us. And then for us to be able to ingest it and then run our algorithms and produce all the products and disseminate them, that's another half hour on top of that. So really, I would say with NISAR, for example, I have heard maybe latencies of down to like 45 minutes in like extreme emergent situations, but that doesn't mean we can create the products that quickly. So really 2 hours is your best bet. Just to give you an example, just a few years ago, or a couple of years ago, the latency, we would expect at least 6 hours for our tropical products. And now we've gotten that down to about 2 or 3. So we've improved as much as we possibly can right now.
Yeah, that sounds like a big improvement just over the tropical stuff. So great, thanks for all that. Well, I'm not seeing any more questions in the chat room, so really appreciate everyone's coming out, and I'll pass it back to Liz for any final remarks. Thanks.
All right, thank you so much, Aaron and Tyler.
Of course, thank you.
Yeah, thank you.
Okay. Thank you for presenting at the SBC today, and thanks, Aaron, for your excellent facilitation during today's discussion. As previously mentioned, please stay tuned for any updates from the Tower S team on next week's presentation. And thank you all for being here and submitting your comments and questions. Have a great day.
Thank you. Bye.
Thanks again.